Hello, everyone. Welcome to section 5.7, where we're going to talk about just some examples of finding zeros of polynomial functions using complex numbers. So no longer just restricted to the real numbers or the real zeros of a polynomial function, but now we can expand our horizons a little bit and find all the zeros of a polynomial function in general, meaning they could be real, they could be complex, they could be purely imaginary. Now, I'm sorry I couldn't be there with you today, but I didn't want to leave you hanging and have to deal with, trying to figure this out on your own. I wanted to give you a little bit of some examples that you could work through along with me, and you can expect similar examples on the study guide and the homework and on the exam too. So 5.7, getting some exercises out of the way, we want to talk about polynomials and the types of zeros that we can find. We'll still look for real zeros, of course, because the real numbers are just a subset of the complex numbers. So when we say complex numbers, we're including that subset of the real numbers as well. So let's take a look at a few examples. Let's see if we can begin by trying to construct a polynomial function with real coefficients that has degree 3 and zeros of x equals 2 and x equals negative 3i. So let's see if we can construct this polynomial that would meet this criteria. Again, when we talk about polynomials, we can talk about their degree, that is the highest power that we see in the polynomial. We can also talk about the zeros of the polynomial. One thing that we want to remember in section 5.7, we saw that real numbers are a subset of the complex numbers. So technically this is a complex zero. It just doesn't have an imaginary part, 0i. This is also a zero of the polynomial. This is purely imaginary, though. It is 0 minus 3i. Now, we have a theorem that says if we have a complex zero, then the complex conjugate of that zero is also a zero. When we take the conjugate of 0 minus 3i, we get another zero of 0 plus 3i. So this would be our third zero. And there's only 3 because when we look at the degree of the polynomial, which is degree 3, we don't want any more than 3 zeros. Now, if I try to take the conjugate of this real number 2, which is 2 plus 0i, the complex conjugate would be 2 minus 0i. That's still 2. That doesn't change anything. So when we look at those complex numbers, if they give us a zero that has an imaginary part, we can automatically pick up a third zero based on the conjugate. And again, just as a quick reminder, when we look at a plus bi or a minus bi, the complex conjugate of a plus or minus bi, which is a complex number in standard form, is a minus plus bi. And I use this notation meaning that if your complex number has addition before that bi, then you switch to subtraction. Notice the real part keeps its value. If a is positive, it stays positive in the complex conjugate. Or if a starts out as a negative number, then a stays a negative number in its complex conjugate. And if you have the minus, then you switch to the plus. So we can pick up these complex conjugates pretty nicely. Those colors are awfully close. I'll go with a purple. So if it's positive, I switch to negative. If it's negative, switch to positive. All right, so we've justified how we picked up that third zero. Let's go ahead and see if we can construct a polynomial that has these features. I'm just going to call it f of x. Now, I'm going to use the factor theorem. The factor theorem states that if I find a zero of a polynomial, then I can construct the factor that corresponds with that zero. If I have a real zero of positive 2, then I must have a factor of x minus 2. Because if I plug positive 2 in, 2 minus 2 is 0. If I have a zero of negative 3i, then I want a factor that has x plus 3i. Since that is an imaginary zero, if I plug negative 3i in, add 3i, that cancels out, I get a 0. Likely with the other positive 3i being a 0 that I picked up from the conjugate. If I plug positive 3i in and subtract 3i, I get 0 in this factor, and everything is 0. Oops, I didn't mean to wipe that away. So this gives us the factors for our function. Now, this is great in factored form, but typically we don't leave things factored across complex numbers like that, or you very rarely see it. But we want to justify that our polynomial does work out so that it does have real coefficients. The coefficients are just the multiples in front of each variable raised to some power. So what I'm going to do is just multiply it out and verify that when I look at that polynomial written out term by term by term and descending powers on x, that I can verify that I don't have any complex stuff left over. I'll just have real coefficients, which are just the multiples in front of each variable x to whatever power. I'm going to hold off on the x minus 2, and I'm going to look at x plus 3i times x minus 3i. I'm going to do that one first because it's a little different, but it is still a FOIL. We're just distributing. So we're going to do the first times the first to pick up x squared. The outer times the outer is minus 3i times x. The inner times the inner is a positive 3i times x. And the last times the last is minus. Now I have to multiply 3 times 3 to get 9. And I multiply I times I to get I squared. Just remember to note that I squared, by definition, is negative 1. So I'm going to rewrite that I squared term. And also, I see stuff that cancels out because I have a negative 3ix and a positive 3ix. I have 0 3ix's. Since I have 0 of them, I'm just not going to write them. They're gone. So this gives us x minus 2. Still not touching that factor. Cleaning up this factor, we will get x squared minus 9 times the quantity negative 1. I'm replacing I squared with negative 1. And you can see that this is building an irreducible quadratic factor of x squared plus 9. Now that's where my two imaginary zeros are coming from. And now I can do the final foiling and verify that I'm not going to have any imaginary stuff pop up in terms of my coefficients. I'm not going to have to worry about complex numbers. First times the first is x cubed. Then I do the outer times the outer, that's plus 9x. Inner times the inner, negative 2x squared. And the last times the last, negative 18. Okay, so I'm just going to write it in descending order and be finished with it, which means we'll have x cubed minus 2x squared plus 9x minus 18. This is the polynomial f of x. That will, and maybe now I'll just rewrite f of x down there. This is the polynomial f of x that I've generated that has those zeros. That's just kind of inherently built into the polynomial the way I figured it out. And it has real coefficients, so I can justify that, yes, I do have real coefficients in the polynomial with degree 3. Yeah, I definitely have a degree 3 because I'm staring at a polynomial with a cube at its highest power. So that lines everything up, and we're happy. So that would be our final answer. If they say to leave it in factored form, then you can leave it in factored form. Typically, we like to leave it in factored form where it's factored across the real numbers. But really, there's nothing wrong with leaving it in the factored form, factored across complex numbers either. But we had to sort of justify that we did have real coefficients, and we have justified that. We had to multiply everything out in order to do that. So can we build polynomials with complex zeros? Yeah, even if they're sort of lazy and don't really give us the other zero, we can find it very quickly since we know that the complex conjugate will also be a 0. Let's do a similar problem, but let's up the degree a little. Let's say we have something that's degree 4. I'm going to pull up. How about this one? Construct a polynomial function with real coefficients that has degree 4 and complex zeros are going to be x is equal to 2 plus I, and x is equal to, let's just say negative I. So it has to have degree 4. Right now we're only staring at 2 zeros, but again, very quickly, since we're looking at zeros that are complex, I can take their conjugates and say that x equals 2 minus I is also a 0. And I can take the conjugate here. Again, this looks like 0 minus I, so I want x is equal to 0 plus I. There's really no reason to write 0 plus I, so I'm just going to write I. So one of them is truly a complex number, and its complex conjugate pops up 2 minus I. The other one is purely imaginary, negative I, so I get the complex conjugate of that one as well, positive I. So I'm going to call my polynomial function f of x. Since I know these are my 4 zeros and I want degree 4, then I've got all the zeros I need, no more, no less. And I'm going to go and say that if positive 2 plus I is a 0, then my factor should look like x minus 2 plus I. Now be careful, because these complex numbers have 2 parts, a real part and an imaginary part. If I take the number 2 plus I and replace x with 2 plus I would then subtract the 2 and subtract the I. So starting with a positive 2 and a positive I have to take away the 2 and take away the I. That's why I have an extra set of parentheses there on that part that has the complex number. Similarly with 2 minus I, if I were to plug in a positive 2 and a negative I would then have to subtract that 2 minus I. Positive 2 and a minus I, now I would have a negative 2 and a negative negative, which is a positive I. So 2 minus I would cancel out with the negative 2 plus I. Doesn't look the greatest, but again, don't worry, we'll multiply it out and build those factors. Negative I is a 0, so I need a factor of x plus I. Positive I is a 0, so I need a factor of x minus I. So verify quickly that if you plug those 4 numbers in, that you would get a nice 0 from each factor. This means that I can now multiply all this out and just get a nice polynomial with powers in descending order. So this is going to look like x minus 2 minus I. When I clear that inner part of those parentheses, x minus 2 plus I. When I clear those inner part of those parentheses. This one we can actually multiply out pretty quickly. X times x is x squared. The outer times the outer will give me a negative ix, but the inner times the inner will give me a positive ix, cancel, cancel. And then we'll get negative I squared, meaning that I'm going to write minus I squared as minus 1. Well, that's just plus 1. Sometimes you might be able to recognize these factors pretty quickly. Like if you have a 0 at 5i and negative 5i, then you'll get factors like x squared plus 25. They'll have the plus in there because we can't really factor the sum of squares across real numbers. That's where we always have to work the complex numbers in, or purely imaginary numbers in sometimes. So big ticket item here is, can we work all this stuff out? Well, they just have 3 terms in each factor instead of 2. So it'll take a little bit of work, just some algebra. X times x is x squared. X times negative 2 is negative 2x. X times I, that's a positive ix. Then I'll go for my negative 2 times x, that's negative 2x. Negative 2 times negative 2, that's plus 4. Negative 2 times positive I, that's minus 2i. Then I'll go for the last piece on the first factor. Negative I times x, that's minus ix. Negative I times negative 2, that's positive 2i. Negative I times positive I, that is a negative I squared, which we just saw was plus 1. Yeah, that generates a really big factor, and the other factor, x squared plus 1, is just going to hang around in this step. But I have 3 terms times 3 terms, so it is a lot of distributing. But the good news is, once we're done doing all that distributing, lots of stuff should cancel out because our final polynomial shouldn't have a lot of i's left over. I see a positive ix and a negative ix. So those are canceling each other out. I see a negative 2i, I see a positive 2i. So those are canceling each other out. And again, the last negative I times the last positive I give me a negative I squared. We never leave I squared. We write that as negative 1, but because of that extra negative, it's now plus 1. So this is great because now I can start to simplify this a little bit and say I have an x squared. I do have a negative 2x and a negative 2x. That's negative 4x. And I do have a plus 4 and a plus 1, so that's plus 5. Again, the x squared plus 1 factor is still part of the polynomial. It's just kind of been hanging out along for the ride. So just to write it all out, we'll have to do a little bit of distributing, but you can see all the complex and the imaginary stuff is gone. We'll get some real coefficients, and then we'll be done with this. So multiplying out, x squared times x squared is x to the 4th. X squared times positive 1 is just x squared. Negative 4x times x squared is negative 4x cubed. Negative 4x times positive 1, that's negative 4x. 5 times x squared, there's 5x squared. 5 times 1, there's 5. I don't need the parentheses anymore, we're good. And just to be nice and write it in descending order, f of x is equal to x to the 4th. Since this list is kind of long, I'm going to scratch them off as I go. They're not canceling, I'm just scratching them off so that I know I caught them. I want to make sure I get all my 4th powers. I want to make sure I get all my cubes. There's only one, minus 4x cubed. There is a positive x squared and a positive 5x squared. So I've got 6x squared. There's a negative 4x. It's the only one that has x in it. And then my constant on the end. Don't forget the constant. That's still part of the polynomial. So here is our function that has real coefficients, verified real coefficients. Yep. We've got all 4 zeros. Check, 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 check. That's how we built it. So that's how we can verify the degree is correct. So everything lines up and we're happy. Good to go. So let's take a look at some different examples. Your answers may vary here for some of these problems because maybe instead of that exact polynomial, you could take that polynomial and just multiply it across the board by a number like positive 10. You just have 10 times the polynomial I have. But that scaling multiple won't affect the zeros because if you multiply everything by 10, then you could have just factored that 10 out. You'd still have the same factors being set equal to 0. Or you could take that polynomial function that I got, you could take the whole thing and chop it in half. It would not change the zeros because you're not changing the x factors that are involved. You would just have half the polynomial I have, but the zeros would still be zeros. It may look a little different when you go to graph it because, again, you might be graphing half of the function I had. Maybe someone else had 10 times the function I had. The graphs would look different because, yes, they are different functions, but it doesn't change the zeros. Those zeros are stuck to the x-axis. Well, at least the real ones are. The complex ones we don't even get to see when we graph the function on the real x-axis and the real y-axis. So answers may vary for some of those first couple of problems that you may come across. Okay, let's say we have the task of, let's say we want to find a polynomial function. With the given degree and zeros. And this time we will just go ahead and, for the sake of not having to write it all out, leave the polynomial in factored form. Meaning we won't have to do all this distributing. They're just saying, hey, go ahead and just find a polynomial that has these zeros. Once you verified those zeros, and you can see that the degree matches the number of zeros you're looking at, that's fine. No reason to do a whole bunch of distributing. We'll save you some time here. So we'll say that we have a degree of 5, and we have zeros of x equals -7, 2i, and let's do, how about 6 minus 3i for our zeros. Okay, so right off the bat, let's catch, we've got one real zero. We're not going to conjugate that and say that we have another zero at +7. That's not how we conjugate complex numbers. If that's the real part, -7, then that's my zero at -7, meaning I have a factor of x plus 7. So make sure you catch that. You don't want to fall into any sort of trap there. Now we have 2i as one of the zeros, so that's going to tell us that -2i is another zero. So that'll build some factors x plus 2i and x minus 2i, where the -2i goes along with the factor x plus 2i, and the 2i would go along with the factor x minus 2i. And the 6 minus 3i, conjugate would be 6 plus 3i. So my factors would look like x minus the 6 minus 3i quantity and x minus the 6 plus 3i quantity. Your factors should always look like x minus something, x minus something, x minus something. I say that, and then you look at this factor and you go, wait a minute, that's x plus something. Well, yeah, because secretly we're doing x minus -7. X minus -7 does generate that factor of x plus 7. So we would leave it in factored form like this. Typically, we don't leave things factored across the complex numbers. If it says to leave it in factored form, I like this, but I'm just going to be a little pickier here and clean up this. I'm not sure if that really changes anything in the grand scheme of things. It's still factored across complex numbers. Am I doing anything fancy? No. Just kind of cleaning up the minuses in front of the extra parentheses. But if you ever see something that says leave it in factored form, I'm totally fine with this. Meaning that I've probably given you too many zeros to make the task short. I've given you too many zeros, and it's going to make the task tedious. You can do it, and I know you can do it. More so, this one's just a check to verify. If given zeros, can you find the rest? Can you write out the proper factors so that you do get zeros when you plug those zeros into your factors? So this is good enough for us for factored form. We don't want to spend a whole bunch of time just distributing. Again, I know you can distribute. My dog is in the room. He might be knocking the camera around, or you might hear him pitter-pattering. My apologies. Don't worry, I'll make him take the test too. Okay, now let's take the reverse of kind of what we've been doing with those couple examples. Let's see if we can start with a function that is given and do the task that we all came here to do, and that is find the zeros. So let's say we have the task of, first they'll help us out, they'll maybe give us one or two of the zeros and tell us to find the rest, and then we'll do an example where we just have to do it from scratch. So let's start with, use the given zeros of f of x to find the remaining zeros. And that means all of them, not just the real ones, but complex ones, all their conjugates, etc., etc. So use the given zeros of f of x to find the remaining zeros. And let's take a polynomial function f of x is equal to x cubed plus 3x squared plus 25x plus 75. And they will tell us that one of the zeros is going to happen at negative 5i. So here's a situation where you've been handed a polynomial function and they have asked you to find the remaining zeros based on at least a little bit of helpful information, like one of the zeros is negative 5i. So the question is, can we do it? Well, we can definitely find one really quickly. We can say that the other zero that goes along with this imaginary zero, negative 5i, is going to be at positive 5i. So we can very quickly pick up another zero, which is great. Now, this thing is a cubic. Since it has degree 3, I know that there's only one more zero out there. Degree 3 tells me I've got 3 zeros to go find. It wants us to find the remaining zeros. Okay, well, I'm close. I've already got the second zero. That's just knowing that the complex zeros come in conjugate pairs. What that tells me is that the last zero cannot be a complex zero with an imaginary part, or it can't be a purely imaginary zero, because then I would also have to pick up its conjugate, meaning I would have to pick up 2. The remaining zero has to be a real zero. I know that just by looking and saying that I have an odd degree. I've already got 2 zeros, and since complex zeros come in pairs, I would have to pick up 2 more if I had actual zeros that had an imaginary part. So I know it's a purely real number that I'm looking for. The last zero must be real. Question is, what could that zero be? Well, you do have some options. At this point now, one thing you can do is look at that rational zeros theorem. Now, when you look at that list of P over Q, P coming from the different factors inside 75, Q coming from, well, our leading coefficient is 1. That might be a long list. That could be hard to try, and that long list may not guarantee you find one of the zeros. Fortunately, okay, that's not going to work. Hey, no squeaking. Unfortunately, one of those zeros on that list, unfortunately, that list might not produce an actual zero that you can use. Unfortunately, you might be stuck not finding a zero on that list. The other thing that you can try is actually taking the zeros that you do know are there and using those zeros to build a factor and doing a little bit of division to find out the last remaining factor. And that's what I'm going to do, just to give us a little more practice, not only with the division, but also, yeah, I know, but you can't have it. Not only to give us a little bit of practice with the division, but also to give us some practice dealing with finding that remaining zero. So here is f of x, which is this cubic polynomial. It can be written in the form x with a plus 5i factor, x minus 5i factor, and one more remaining factor that is necessarily going to have to spit out a real zero, meaning that what you're going to have to do is find that remaining factor. Well, these two factors are going to produce x squared plus 25 as an irreducible quadratic. I know that because if I FOIL these out and do the distribution, then I'm going to have x squared. I'm going to subtract this negative 5i. I'm going to add this positive 5i. They'll cancel out. 5i times negative 5i, that's negative 25i squared. Well, I squared is negative, so I change that to a plus 25. So this shows me the factor that I need to divide into f of x. And since I know that those two imaginary numbers are zeros, then when I do this division, my remainder has to be 0. That's the remainder theorem. If your remainder is 0, then you know you have the right factor. If you have the right factor, then you know you've got zeros. So I'm kind of doing that backwards. Zeros to the factor. Factors, I'll get 0 remainder. Whatever's left over after that division will just be something that's linear, because I'm taking a cubic polynomial, dividing it by a quadratic, meaning the last thing left over will just be some sort of linear factor of x. When we do this division, we want to know how many times x squared plus 25, which is a binomial, will go into this whole polynomial. Well, I'm concerned with the first terms canceling out. I want to reduce the power on this polynomial by dividing out. So I'm going to say that x squared plus 25 will go into x cubed plus the rest, another x times, because that does generate x cubed. But I still have 25x. Make sure you put that in the right column when you're doing the division. You want to cancel out the right terms now by taking the difference. I want to see what the difference is. So I'm going to do x cubed minus x cubed. That's great, that cancels. And then I'm going to do 25x minus 25x. Well, that just is kind of us getting lucky. That also cancels. And now we can say that we've got still this 3x squared. We didn't do anything with it. It doesn't just disappear. It's still there. And we've got this positive 75 constant. Doesn't just disappear. It's still there. So I drag it down and I repeat my process. Is there anything I can do to still divide x squared plus 25 into 3x squared plus 75? And the answer is yes, I can do it another 3 times. So I can multiply 3 times x squared. That generates 3x squared. And that means x squared can go into 3x squared another 3 times. But again, it's a binomial. So I have to do 3 times 25. That is 75. So we're getting a little lucky there. But is it really luck when we know that this was one of the factors? Everything should be canceling and giving us a 0 remainder. No, that's not luck. That's just math. We know that we should get a 0 remainder because we're looking at a factor. And we built that factor based on zeros of that polynomial, so we know it's going to be a 0 remainder in the end. The thing that we want is we want to take this x plus 3. That x plus 3 is the remaining linear factor that we were looking for. I really wanted to know what that last factor was, because right now I'm staring at this irreducible quadratic coming out of this cubic. Aha, the last factor must be linear. The last factor must be x plus 3. Thus, the last 0 must be negative 3. So now I can say that, and we'll just summarize over here. Thus, the zeros of f of x are x equals negative 3, coming from the factor of x plus 3, positive 5i, and the one that was given was negative 5i. That one's not really something you have to write again since it was given, but I'll write it again just to sort of summarize everything up. Now this one, they give you a little boost in the beginning. They said, "Oh, I found one of the zeros for you. Can you please find the rest?" And there were only 2 more to find. That's not too terrible of a challenge to do. What if they don't give you any of the zeros? What if they just say, hey, go for it. Here's a polynomial, just go right ahead. Knock yourself out trying to find the zeros. That could be a little trickier. So let's take a look at an example where they give us a polynomial, and that is our task. Our task is to start from the very beginning and work our way through. Let me see if I can pull up an example here. Let's start with, while we're at it, toss that. Let's say our task is to solve the polynomial function. which means we are starting from scratch, and we're going to take x to the fourth minus 1 and set it equal to 0. This is starting right from the scratch and trying to solve a polynomial function like this. Now, at this point, you have different techniques that you can use. One of those techniques that you can use would be kind of right off the bat trying to add 1. And then once you've got that, now you have to take the fourth root on both sides. This might not be something that we've done before, but when we take the fourth root of x to the fourth, then when we do this, since this is an even indexed root, we do have to be careful because we have to take the positive or the negative version, meaning that x is either equal to positive or negative 1. That's one great strategy because that gives us 2 of the zeros. What could the other 2 zeros be, though? It's a fourth degree polynomial. I should be able to find 2 more. Well, what we can do is take this x to the fourth minus 1 and rewrite it as x minus 1 because we have a 0 at positive 1, x plus 1 because we have a 0 at negative 1. But notice it still leaves behind some sort of factor that still needs to have 2 zeros in it, so it's leaving behind some sort of quadratic factor. Is it an irreducible quadratic? Is it a reducible quadratic? These are the questions that we have to ask. Am I getting a pair of complex zeros? Or am I getting 2 real zeros? Or is it possible that I can get 1 more real zero and 1 is a complex 0? Well, immediately no. I can eliminate that because complex zeros have to come in conjugate pairs. So I either have 2 of them, which are complex and do have an imaginary part, or I have 2 real zeros and I need to go find them. So we could take x to the fourth minus 1. We'd have to divide once by the x minus 1 factor, again by the x plus 1 factor. But before I go doing that, I can try and take x to the fourth minus 1 equals 0 and look at it a little differently, in this case as the difference of squares. And it may not be very apparent at first, but if I look at x squared squared, that is x to the fourth. And of course 1 squared is 1, so technically that's still the difference of squares. And I would have x squared plus 1 times x squared minus 1 equals 0. Aha! This x minus 1, x plus 1, that is where these 2 linear factors are coming from. That's the difference of squares again. This one is the sum of squares. That one I can't factor across real numbers. I'm going to have to do something with that factor. So these are tricks that you have that you can use, and some of these tricks are from previous classes like college algebra, algebra 1, algebra 2. So you still can't forget those tricks. They're part of your repertoire. This x squared plus 1 should be donating 2 more zeros, and there it is. If I subtract 1 on both sides, sort of like what I did over here at first, I'll pick up 2 more zeros because now x squared has to equal negative 1. What that means is that x squared, I'll take the square root, meaning on the right-hand side I have to take, and don't forget, plus or minus the square root of positive 1. We don't need the 2 in the index there, the square root's understood. Which means now I can say that, or sorry, not positive 1, negative 1. Almost forgot the negative on there when I subtracted. Plus or minus the square root of negative 1. That means x is equal to plus or minus I. Aha, there's the other 2 zeros that we have. So now we know that our function, or our polynomial, has roots, or aka zeros. When I look at all these factors, I can find out that the remaining factor was an irreducible quadratic. That's the one that was spitting out a pair of complex zeros. So these solutions are x equals, and we can kind of condense it and say plus or minus 1, plus or minus I. There's all 4 of our solutions to x to the fourth minus 1 being equal to 0. So sometimes factoring can get you through, and we could see things like difference of squares, difference of cubes, sum of cubes. We could see things that maybe have 4 terms, and we can possibly split them down the middle and do what we call factor by grouping. That's still a great technique, but again, that one's not bulletproof. Sometimes it works, sometimes it doesn't. We have that long division or synthetic division if you're dividing by a nice linear factor, that you can take something and divide by one of the factors to knock that power down to a smaller polynomial. And that really is the name of the game. If you start out with a polynomial of degree 10, 11, 12, you want to start knocking those numbers down, 9, 8, 7, 6, until you can finally recognize all the zeros of that polynomial. Sorry for the squeaking in the end. But that's pretty much it. I just wanted to go through a couple of examples to give you guys some practice for the exam that's coming up. This may only be like 1 or 2 questions at most 2 questions. And then this will give you, hopefully a good overview of kind of growing up from solving linear equations to then you focus on solving just quadratic equations. Once you get past quadratics and you get into cubic, 4th power, 5th power, 6th power, 7th power, 8th power, etc., you don't want to spend all day looking at just cubics, just 4th power, just 5th power, just 6th power. You want to say, okay, is there a more general strategy that I can apply to every polynomial? And the answer is, yeah, we just kind of use these tricks that we have. A little bit of factoring, difference of squares, difference of cubes, sum of cubes, factor by grouping, long division to knock the powers down, rational zeros, P over Q. At least I have a list and I can look at that list. It's a finite list. I can check and see if I can find some zeros. If I do find a 0, then I found a factor. If I found a factor, I can divide. I can knock that polynomial down and just repeat the same process all over again. Make a new list of possible zeros. And then again, etc., etc. Keep doing that until you keep knocking it down. Unfortunately, we don't go into anything beyond that in terms of like using like computer algebra system or some sort of software to do like numerical approximations of zeros. That stuff can be pretty tricky. So that's something that may be reserved more for like a 3,000 or 4,000 level course. But these aren't the only techniques that we have. But strictly speaking, algebraically, these are the techniques that we have. Otherwise, you'd have to start digging into some technology and you have to learn a little more stuff to make things hopefully a little easier on you. But that said, again, just wanted to give you some examples. Thank you guys for watching, and let me know if you have any questions. Shoot me an email, and I'll try and get back to you as quickly as possible. So thank you very much.